Good evening, students. Today we'll see some topics which we have left off in the second module. Uh, I hope you remember all the transforms that we have seen here. So these are the image transforms that are listed in the text. And out of this, we have seen orthogonal, sinusoidal, basis function. Now, I hope you remember what is a basis function. If you have a Fourier transform, you have a basis function as a matrix. For a 4-point Fourier transform, we have derived a 4x4 basis function to transform an image. So that 4x4 matrix is called the basis function. So such transforms are called orthogonal sinusoidal basis function. Okay. So under this comes Fourier transform, discrete cosine transform, and discrete sine transform. Of course, we have to study Fourier transform and its properties, and also discrete cosine transform. Then we have non-sinusoidal orthogonal basis function based transforms. So under this, we have Hart transform, Walsh transform, Hadamard transform. We have to study these three transforms. Then basis function depending on statistics of input signal. Under that comes KL transform and singular value decomposition. Then you have directional transformation, and under this we'll be studying only House transform. So today we'll try to finish KL transform and singular value decomposition. So let us go to the place where KL transform is given. So the expansion for KL transform will be Karhunen-Low transform. Okay. So KL transform is a linear transformation, and the important thing about this is there is no fixed basis function. Instead, this transform derives its basis function from the given image. So when I say this, the basis function of the KL transform are orthogonal eigenvectors of the covariance matrix of the data set. So just remember that these things are important. What are they? You have to find the covariance matrix, and the basic functions of the KL transform are orthogonal eigenvectors. So what all should you find out? You have to find out the covariance matrix and also the orthogonal eigenvectors of the covariance matrix. Okay. Then KL transform optimally decorrelates the input data. What do you mean by decorrelates the input data? So KL transform has its axis in the direction of the maximum variance of the data. So after a KL transform, most of the energy of the transform coefficients is concentrated within the first few components. This is the energy compaction property of a KL transform. So what all things do you understand from this chapter, from this paragraph? You can see that you have to derive the covariance matrix. From the covariance matrix, you have to find the eigenvectors to form the basis function. And what is the advantage of KL transform? Most of the energy is concentrated within the first few components. And this is the energy compaction property of a KL transform. Okay. Then drawbacks of KL transform is input dependent, and the basic function has to be calculated from each signal model on which it operates. KL bases have no specific mathematical structure that leads to fast implementations. So as I told you, in Fourier transform, 4-point Fourier, if it is a 4-point Fourier transform, you have a 4x4 matrix. If it is a 8-point Fourier transform, you have an 8x8 matrix as the basis function. After you multiply the given input with the basis function, you will get the corresponding transformed output. Isn't it? The same thing applies for Walsh transform and Hadamard transform also. But in KL transform, you have to derive the basis function from the given input signal. Okay. Then the KL transform requires M squared multiply add operations. Whereas DFT or DCT requires only log base 2 of M multiplications. So this is the difference in calculation. Applications. We have seen k-means clustering. For clustering analysis, KL transform is used in clustering analysis to determine a new coordinate system for sample data, where the largest variation of a projection of the data lies on the first axis, the next largest variance on the second axis, and so on. Because these axes are orthogonal, this approach allows for reducing the dimensionality of the data by eliminating those coordinate axes with small variances. This data reduction technique is commonly referred as principal component analysis. Okay. This is what I told you. This is a transformation which depends on the variance in data. So the first axis will be taken along the direction of the maximum variance. So that is called the first principal component analysis. First principal component. Next axis will be taken in the direction orthogonal to the first direction. That will be the second principal component. Okay. So this data reduction technique is commonly referred to as principal component analysis also. So image compression. So this is the first application. Second one is image compression is heavily utilized for performance evaluation of compression algorithms, since it has been proven to be the optimal transform for the compression of an image sequence, in the sense that KL spectrum contains the largest number of zero-valued coefficients. So we'll see an example to study the KL transform. Remember, this exam, such problems are often asked in the exam. So you try to do all these things step by step. So perform KL transform for the following matrix. This is the given input image, x equal to 4, minus 2, minus 1, minus 3. So first step will be formation of vectors from the given matrix. So the given matrix is a 2x2 matrix. Hence, two vectors can be extracted from the given matrix. Let it be x0 and x1. So x0 will be the first column vector. X1 will be the second column vector. So do you understand this? If you are given a matrix, you have to divide the matrix into column vectors. The number of column vectors will be equal to the number of columns in the given matrix. Then determination of covariance matrix. How will you determine the covariance matrix? Covariance of X will be equal to expectation of X into X transpose minus X bar into X bar transpose. So X bar will represent the mean of the input matrix. Okay, so first you have to find the mean. You have two matrices now. You have to find the mean of these two matrices, because the final formula for covariance is covariance of X equal to expectation of X into X transpose minus X bar into X bar transpose. X bar denotes the mean of the input matrix. The formula to compute the mean of the given matrix is given below. So X bar equal to 1 by M, K equal to 0 to M minus 1, Xk. So this is the formula to find the mean of the matrix. That is, in the formula for covariance, you have an expression for mean, X bar into X bar transpose. So you have to find the mean first. So X bar will be equal to 1 by M. M will be the number of matrices or number of vectors. K equal to 0 to M minus 1. So what will be the value of K here? K will be 0 and K will be 1. Okay. So this is nothing but 1 by 2. For M, you have to substitute 2. K equal to 0 to 1 because M equal to 2. So K equal to 0 to 1. Xk, which means 1 by 2. For K, you substitute 0 and 1. X0 plus X1. So this will be 1 by 2 into 4 minus 1. That is the value for X0. And minus 2, 3. This is the value for X1. So this will be equal to 1 by 2, 2, 2. And this will be equal to 1, 1. The mean value is calculated as X bar equal to 1, 1. Now multiplying the mean value with its transpose yields E mean value transpose multiply. So X bar into X bar transpose 1, 1, 1, 1. 1, 1. This will be the answer. You have to multiply 1. This will be 1. This will be 1, 1. So this will be a 2 by 2 matrix. Now proceed with. Now you have found out the value for this part. This part shows this one. Now you have to proceed for finding out this part, X into X transpose. So X into X transpose, you can use this formula. You have to just substitute the values here. K equal to 0 to 1, Xk, Xk transpose. So this will be X0, X0 transpose plus X1, X1 transpose. So find out the values. Reduce it to the lowest term since it is a expectation. So here you can divide by 5 since it is an expectation. So this will be your expected value of X into X transpose. Now you can combine these two values and find the covariance matrix. So you'll get 1 minus 2 minus 2 0. Then determination of eigenvalues of the covariance matrix. So I hope you know what an eigenvalue is. So covariance of X will be equal to lambda into I, where lambda is the eigenvalue, I is the identity matrix. So that is the formula for covariance, so eigenvalue. So covariance of the eigenvalue of the covariant matrix can be found out using this equation. Covariance of X equal to lambda into I, where lambda is the eigenvalue and I is the identity matrix. So covariance of X minus lambda I will be equal to 0. You have to take the determinant. So substitute the value for covariance of X minus lambda. For the identity matrix also substitute the value, you equate it to 0. Do the multiplication. Combine these two. You'll get this value. And this, if you take the determinant, you will get a equation, quadratic equation. You can solve the quadratic equation for finding the value roots of lambda. So the value of lambda that you get, this is a squared equation. So you get two values for lambda. Lambda naught equal to 2.5615 and lambda 1 equal to minus 1.5615. Therefore, the eigenvalues of covariance of X are lambda naught equal to 2.5615 and lambda 1, this is lambda 1 equal to minus 1.5615. Okay, so now we have found out the eigenvalues. From the eigenvalues, you have to find out the eigenvectors. Okay, so if I tell you an example, if you take the Cartesian coordinate system, for the X direction, you always write it as X into I. Y direction, you write it as Y into K. Z direction, you write it as Z into K. Now, what do these I, J, and K represent? They represent the vectors indicating the respective directions. Similarly, here also, for the eigenvalue lambda naught, the eigenvector will be phi naught. So substitute phi naught in this equation. Covariance of X minus lambda naught into I into phi naught equal to 0. So covariance of X minus lambda naught I naught into phi naught will be equal to, substitute the values for covariance of X and substitute the value for lambda naught. So lambda naught will be 2.5615. So covariance of X minus 2.5615 0 0 2.5615 and phi naught you can split it into 2 because this is a 2-row equation. You can write it as phi 0 0 and phi 0 1. And phi 0 1 you can take it as a free variable. Take phi 0 1 as a free variable and give it the value 1. The value of phi 0 0 will depend on the value of phi 0 1. Okay. So multiply these equations. Minus 1.5615 into phi 0 0 minus 2 into phi 0 1. That will be equal to 0. So phi 0 0 will be equal to 2 by minus 1.5615. Okay, because phi 0 1 will be 1. You are fixing the value of phi 0 1 as 1. So you can find out the value of phi 0 0 as 2 by, bring this to the side, bring 1.5615 to the bottom, you will get 1.2808. So the eigenvector phi naught will be equal to minus 1.2808 and 1. Phi 0 0 will be 1. Is it clear? Now we have found out phi naught. Similarly, you have phi naught will be the eigenvector in the direction of lambda naught. Similarly, you have one more eigenvalue, phi 1. So the value of phi 1 is minus 1.5615. So the direction eigenvector in the direction of phi 1 will be, in the direction of lambda 1 will be phi 1. So follow the same procedure you followed for finding out phi naught. Split this vector into two, phi 1 0 and phi 1 1. Find out the value of phi 1 0. So the eigenvector phi 1 will be 0.7808 and 1. Follow the same procedure you followed for finding out phi 1. Okay. You can just see this. You're inserting this phi 1 here, substituting the values, multiplying by lambda 1, you get these values. So phi 1 0, phi 1 1, 0 0. Solve this equation, you'll get the value for phi 1. Okay, so now where have we arrived? We have found out the values for phi naught and phi 1. Okay, now we have to normalize these eigenvectors. Because we are using free variables, the eigenvectors will be at some point in space. You have to make a comparison, you have to normalize all these values. Normalization means you have to divide by the maximum value. So to normalize phi naught, you are taking the norm of phi naught. So this will be phi naught by norm of phi naught, 1 by root of phi 0 0 square plus phi 0 1 square into phi 0 0 phi 0 1. So phi naught by norm of phi naught will be 1 by root of minus 1.2808 the whole square plus 1 square into minus 1.28081. So this will be equal to minus 0.7882, 0.6154. So this will be the normalized value for phi naught. Follow the same procedure for phi 1. This will be the normalized value for phi 1. Okay. So this is the final step for writing the transformation matrix. Then the step 6 will be KL transformation matrix from the eigenvector of the covariance matrix. So from the normalized eigenvector, we have to form the transformation matrix. So the transformation matrix T will be equal to, this will be phi 0, this will be phi 1. Okay. Now, if we have to check whether this transformation is reversible. Any transformation is valid only if it is reversible. That is, you should be able to get back the original data when you perform the inverse transformation. So here, when you multiply T by T transpose, the value should be equal to I, identity matrix. So we are doing that here. This is your T multiplied by T transpose. You will get 0.99900, 0.999. So this will be 1001. So this will be the KL transformation of the step 7. Now you have found that the kernel is correct. Kernel or the basis function for the KL transformation of the given matrix. You have derived it. This is your kernel. You have proved that the kernel is correct by getting the identity matrix at the output. And the step 7 will be to do the transformation of the input image. So the input image, one second. Okay. So you're transforming the input image. So this is the first vector. Either you can transform it by combining x0 and x1 and multiplying it by the kernel, or you can do it separately also. So when you do it separately, first you take the first vector, transformation of x0. This is your transformation matrix. This is your first vector. You get this value. This is the second vector. You get this value. Just see whether it is the same as the input. Your input was -4, 3, 1, 1. Is it correct? Sorry. This is your transform matrix. This is the KL transform matrix. Now, to perform inverse transformation, you have to multiply it by the transpose of the transform. So x0 will be T transpose y0. So T transpose y0 will be equal to this one. X1 will be T transpose y1, that will be equal to this one. You combine it and write. For 3.9, you can write 4. Minus 1.9, you can write -2, -1, and 3 here. Okay, so this will be your KL transformation. You can try out this problem. It's a work example given over here. Okay. If you have any doubts, we'll discuss it in the class. When you please write this as your tutorial 10. Okay, thank you.